Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. Now, let me ask you a question. How many times have you watched the TV, listened to radio, surfed the web, and something pops up that catches your curiosity? Something about technology, about science, about medicine, about the future, and you're all alone. You have no one to talk to. It's just you and the internet, you and the TV set. Well, here's your chance to talk back. And no question is too dumb to put on national radio. As I mentioned years ago, there was a 23-year-old gentleman who had to go home because there was a disease affecting his university. He had a lot of free time. And one day he was walking down a country road and he saw an apple fall. Well, nothing strange about that. And then he looked up and he saw the moon. And then he asked himself a question which changed human history. And that question was, if an apple falls, does the moon also fall? Now, that's a stupid question. That's the question that even a child would be embarrassed to ask. Does the moon also fall like an apple? Well, that young gentleman said, yes, the moon is also falling. It's in free fall, just like the apple. And then he went out to try to calculate when this moon would fall past the earth. And then he realized that, gee, the mathematics of the day were not sufficient to calculate that. So he said to himself, I'm going to create a new mathematics. That new mathematics was called calculus. That man was called Isaac Newton, the greatest scientist of all time. And looking at a child's question of the falling moon, he was able to get the law of gravity and able to work out the majesty of the universe itself. Every time we launch a space probe into outer space, it's compliments of Isaac Newton's laws of motion. You know, we can shoot a space probe right through the rings of Saturn. That's how accurate the laws of Isaac Newton are. And we can do that because a 23-year-old gentleman asked himself a simple question. If an apple falls, does the moon also fall? Okay, well, let's move right on now and take the first listener phone call.
Hello, Dr. Kaku, Albert here in San Jose, California. Hey, listen now, I heard you on another show via YouTube. That's how I, catch your programs. And you were talking about laser projection. That's something new. I never caught that, to where they actually can project the digitized person through space at the speed of light. And that makes a lot of sense to me. Can you just go ahead and elaborate more and more and explain it more to us? Would it be our conscious, or would it be just the copy that you would be able to transverse these vast distances? Thanks a lot, and have a good day.
Yes, in my book, The Future of Humanity, I talk about something I call laser porting. Well, first of all, believe it or not, we're gradually going to the point of digitizing the human being. That is, creating a digital copy of ourselves that lives forever. This is sometimes called digital immortality. For example, when you go to the library today, you take a book out about Winston Churchill. In the future, near future, you will talk to Winston Churchill because he's been digitized. Everything known about him, his voice, his writings, his speeches, his personality, his quirks, his stories, everything known about him has been digitized, and you'll talk to a hologram, a holographic image that looks just like him, talks like him. And look, I would love to talk to Einstein. I would love to have an opportunity to sit down and talk to a digitized version of Einstein that has all his writings, all his thoughts, all his tapes, everything, his books, his theories, all of it contained in a digitized image, which is animated, talks just like him, looks like him. In fact, one day you may be digitized as well. All your credit card transactions, all your Instagram photographs, everything known about you, your voice, your jokes, your past, what people say about you, digitized, and this is going to happen very soon. not decades into the future. Eventually, we will have the Connectome Project where we will digitize the human brain. Already, we've digitized the brain of a fruit fly. We know that a fruit fly has 100,000 neurons in its brain, and we've digitized it. How do we know? Because we've sliced up, believe it or not, we have sliced up the brain of a fruit fly, analyzed the connections, reconnected the neurons in the computer, and we recreated the brain of a fruit fly, 100,000 neurons. Now, our brain is more complicated. We have 100 billion neurons, not 100,000 neurons. But one day, that'll be digitized too. Now, what do we do with it? First of all, when you die, all your thoughts, memories, personality die with you. However, if you've been digitized, that digital version lives forever. And what do you do with it? Well, one thing you can do is to create a library of souls, whereby you can talk to people who died hundreds of years ago because they've been digitized in the past. So your great-great-great-great-great-grandkids may be able to talk to you, their ancestor. Now, what else can you do? Another thing you can do is to shoot it into outer space. Information can be placed on a laser beam. Laser beams can be shot to the moon, where in 1 second you are on the moon. I repeat, 1 second you, quote-unquote, are on the moon. Your personality, your thoughts, your dreams, everything on a laser beam shot to the moon. In 20 minutes, you're on Mars. In 8 hours or so, you're on Pluto. In 4 years, you're on the nearest star. No problems of weightlessness, radiation, accidents, meteorites. No, none of that. You simply hop into the laser beam and you emerge on Mars. Well, let's take a short commercial break, and I'll talk about whether this already exists. Maybe the aliens have already Welcome back to Science Fantastic with Professor Michio Kaku. Yes, if you want to get on national radio, give us a call at 612-564-8135. Before the commercial break, we had a question about laser porting. How do we reach the stars without a rocket ship? Well, rocket ships are clumsy. You can have accidents, radiation, meteorites, and it takes forever to reach outer space with a rocket ship. Why not do it on a light beam? That's what I call laser porting. One day we will digitize the human body. Everything known about you will be digitized. We can put that information on a laser beam, like we do the internet, shoot it into outer space. 1 second you're on the moon. 20 minutes you're on Mars. In 4 years, you're on the nearest star. This is the most convenient way to conquer the universe. Now, once you laser port to the moon in 1 second, you download your laser information onto a mainframe computer. Then the mainframe computer controls an avatar which is a robot that looks just like you. The only difference is that it's super handsome, super beautiful, and it is immortal, and it has superpowers. You become Superman and Superwoman on the moon. This means you can explore the universe in an afternoon. Think about that. 1 second you're on the moon, 20 minutes you're on Mars. You can easily explore the solar system in an afternoon. Have breakfast in New York, have lunch on Mars, have dinner on Venus, and come back for dinner back on the planet Earth. Sound preposterous? It is well within the laws of physics. Now let me stick my neck out. Now. I think that this may already exist. That's right. This may already be a reality. Perhaps aliens from outer space, more advanced than us, have already created a highway, a laser highway containing millions of souls that are being laser ported across the galaxy at the speed of light. And then the question is, are we smart enough to even know about it? Are we smart enough even to know of its existence? And the answer is no. We are so primitive that right next to us, there could be a superhighway of alien souls being laser ported across the universe, and We're too stupid to know it. But think about that. If you could laser port yourself across the solar system, you could journey to many asteroids, many planets, just in an afternoon. On each asteroid, each planet, you would have superpowers. You wouldn't have to breathe the air. You would be able to lift objects that are extremely heavy and perform feats like Superman because you would be robotic. You would have the body of a robotic avatar. But look, just like you. So you would never know that it's not really you. And then the question is that really you? Well, to paraphrase Bill Clinton, it all depends on how you define you. How do you define you? Are you nothing but a biological entity, in which case we're talking to a tape recorder? Or are you the sum total of all the information known about your personality, your wants, your dreams, your desires, your history, your personality, your friends, all of that digitized? So the question is, what are you? If you can be digitized, it means you can live forever. You can travel the universe by laser beams at the speed of light. And how long would it take from your point of view? It would be an instant. You simply get on the laser beam and immediately you wake up on the moon, you wake up on a distant star, you wake up in another galaxy. All of that complements of the laws of physics. Okay, let's move on now to the next listener phone call.
Yeah, this is Reg Proctor calling from Tempe, Arizona, and I have 3 questions. The first one is, people say you can't, with entangled particles, you can't have instantaneous information transfer. And the likening to it is that, well, then you have to tell someone you looked at it, and that information has to go at the speed of light. What if on each end people had an agreed time, maybe like a heartbeat, right, where it's just happening every second or something, that a particular particle is going to be looked at, then you wouldn't have to transfer that information. Could you then be able to one end look at what the other end did and transfer information faster than the speed of light? That's my first question. In other words, the timing being pre-agreed might get around having to send that information. Secondly, I know this might be a potential alternative to string theory, so I don't know if you actually want to answer this, but have you ever looked at Garrett Theses, the eighth theory, which he quaintly terms an exceptional theory of everything? And if you have, I'm just curious if you have any thoughts on it. I think it's quite interesting, but obviously it's nowhere near fleshed out enough to be mainstream at the moment. So those are my 3 questions, and thank you very much for your radio. I love listening to it, and I'll be listening for long into the future.
Okay, well, let me take a crack at some of your questions. First of all, we get a lot of questions about entanglement, so let me explain how that works. First of all, it was Einstein himself in 1935 who published a paper trying to destroy the quantum theory. So Einstein said, let's take, for example, 2 particles of light, 2 photons, 2 electrons, 2 anything, and put them very close together so they vibrate in unison. So we have 2 waves describing 2 particles vibrating together in unison. Then separate them. According to quantum mechanics, an umbilical cord, an invisible umbilical cord, emerges connecting the 2, such that if you jiggle 1 electron, then the other electron senses that instantly, faster than the speed of light. In fact, you can separate these 2 electrons by a galaxy, so that at one point in the galaxy you jiggle it, and the other electron on the other side of the galaxy instantly senses it. So, aha, said Einstein, this violates relativity, therefore it's wrong. So Einstein relished the idea that the EPR experiment, Einstein-Podolsky-Rosen experiment, destroyed the quantum theory because information was traveling faster than the speed of light, and Einstein said, ha! Nothing can go faster than the speed of light. Well, sorry about that, Albert. This experiment has been done. And it turns out Einstein was wrong. Sorry about that. There really is something which goes faster than the speed of light. But you know, Einstein has the last laugh. That's right. Einstein still has the last laugh. Wherever he is, he's grinning someplace because you can calculate the rate at which this information is traveling, and even though it's instantaneous, the information is useless. It is useless, random information. You cannot send Morse code. You cannot send a television program. You cannot send the internet on this device. So Star Trek fans, of course, would love to have a device that allows you to contact Federation headquarters at the speed of light. And they think that maybe entanglement will do it. Well, on Star Trek, they talk about subspace. Subspace communicators allow Captain Kirk to talk to galactic headquarters at the speed of light instantly, faster than the speed of light. Well, sorry about that. It turns out that quantum entanglement does not work faster than the speed of light for usable information. Now, here's an example. Let's say you have a red sock and a green sock, and you put one sock on red, and the other sock is going to be green. You got that? One leg you put a red sock, and the other sock you put a green, or vice versa. Let's say one day a friend of yours does this, putting on socks, and you lift up one pants leg. It is green. Now, what is the color of the other sock on the other leg? Well, obviously it's red. Any idiot knows that, right? Now, the question is, how fast did you know that? Once you knew that one sock was green, how fast did you know that the other sock was red? Well, instantaneous. Einstein would say, aha, this did travel instantaneously, faster than the speed of light, but it is useless, random, useless information. So sorry about that. You cannot go faster than the speed of light with information. Einstein has the last laugh. Welcome back to Science Fantastic with Professor Michio Kaku. Well, the lines are open. You can give us a call at 612-564-8135, or you can also go to my website, mkaku.org, mkaku.org, and listen to previous shows of Science Fantastic. And before the break, we had a very interesting question. First of all, information. Can information travel faster than the speed of light? Well, the answer is yes, but it is useless information. It is gibberish. It is random information, not usable. That is, you cannot send Morse code. You cannot send tomorrow's stock market quotations. You cannot send tomorrow's Wall Street Journal via quantum entanglement, which does send things instantaneously, but is useless. Random information. Sorry about that. So if you're a Star Trek fan, we still don't know how to make a subspace communicator that allows you to talk to someone faster than the speed of light. Now, the questioner had yet another question, and that is, well, he knows that I work on string theory, which is the leading candidate for a theory of everything, but he asked, what about another theory? Well, I'm not familiar with the theory that he mentioned. However, let me say this. So far, scientists agree that the unified field theory, that is, string theory, seems to work. It's very hard to test, in fact, impossible to test with today's technology. It predicts many universes, not just ours, so there are criticisms of string theory. But what about an alternative? To my knowledge, and correct me if I'm wrong, to my knowledge, there is no alternative. All the other proposals, including things like loop quantum gravity, do not give you a theory of everything. So what is the bottom line? What's the problem? What is the bottom line for a theory of everything? A theory of everything is actually quite simple. It has to include two things, just two things, and you too could claim to have a unified field theory. First, it has to include the standard model of the quantum theory, with all the quarks and all the mesons and all the leptons. All of that has to be included in the standard model in any unified field theory. It is a theory of almost everything. Second, it has to include gravity, a quantum theory of gravity. If you put these two together in a finite form, you will be recognized not just as a Nobel Prize winner, you'll be recognized as the next Einstein. So far, the only candidate is string theory, though it is not testable, and especially with today's technology, maybe tomorrow's technology, but not today. And so far, there are no other alternatives. All the other so-called alternatives have either shown to be incomplete or mathematically inconsistent. Sorry about that. Okay, well, let's move on to the next listener phone call.
Hello, Professor. My name is Steve, and I'm calling from Hungary. So, after thinking about Fermat's principle, I got a question popped up in my mind, which is, how does light know which is the shortest way to take? Thank you, and I'm really a big fan of yours.
Well, a call from Hungary. That's one of the advantages of being on the Internet. You get instantaneous communication around the world. Well, first of all, we have something called optics, a theory that was worked out by the Arab and Greek astronomers centuries ago. And one of the principles of optics is that light takes the shortest path between 2 points. Now, here's a question that is sometimes given to high school kids. Take a mirror. Oh, we have another short commercial break that we have to take, but after that, we'll ask a question. Does light always take the shortest path between 2 points? Welcome back to Science Fantastic with Professor Michio Kaku. Once again, if you want to get on national radio and ask a question that's always been bothering you, then give us a call at 612-564-8135. And all we ask is that you leave your name, call letters to the radio station if you're listening to one, and the city you're calling from. And perhaps you can ask that question. Make that comment and get your thoughts heard on national radio. So once again, the number to call is 612-564-8135. Well, before the break, we had a question that came in, and that question comes from optics, that is the theory of light, which we teach here at the college. And that is, well, light. Why does light take the shortest path between 2 points? If I have point A and point B, and you ask, what is the shortest path between point A and point B? It would be a straight line. Now let's say you take a mirror, and you have point A above the mirror, and point B a distance away, but also on top of the mirror. And a light beam goes from point A, bounces off the mirror, and then hits point B. And then the question is, what is the shortest path between point A, the mirror, and point B? Well, at first you may say to yourself, that's really hard. I mean, you would have to draw all the light beams that go from point A to the mirror and point B. Well, no. Get a sheet of paper and draw the mirror, a straight line. Draw 2 points next to the line on the right-hand side, point A and point B. And then draw a line that goes from the point A to the mirror, bounces off the mirror, and goes to point B on the same side of the mirror. You may say to yourself, well, that's very difficult. How do you calculate the shortest path between point A and point B? Well, what you do is you get a mirror and simply draw the mirror image on the left side of the mirror. So point A now has a mirror image on the left side of the mirror. Point B has an image on the left side of the mirror at all. Now draw a straight line between point A and the mirror image of point B, and bingo, you have the answer. It is a straight line that goes from point A through the mirror to the image of point B. So light really does take the shortest path between 2 points. Why? Well, that's the principle of optics, but it also comes out of something called Maxwell's equations. You see, the laws of light obey an equation that is well known, has been known for 150 years, and it's called Maxwell's equations. Maxwell's equations are so powerful that they're used in lasers, in radar, in telescopes, microscopes, You name it. Anything involving electromagnetic radiation is described by Maxwell's equations. In fact, Maxwell's equations are so powerful that Einstein was able to extract from it the consequences of light traveling at the same velocity in any inertial frame. And that became the basis of relativity. And so the reason why light behaves the way it does is because it obeys a higher equation called Maxwell's equations. Now, this means that other particles have their equations as well. The electron has its equation called the Dirac equation. The Dirac equation allows you to calculate the properties of electrons anywhere in the universe, the Dirac equation. And then the question is there an equation which describes all particles? That would be the unified field theory. So far, the only theory which allows you to describe all particles by an equation is string theory. Okay, well, let's move on now to the next listener phone call.
Hello, Professor Kaku. This is Paul Yazdani. I listen to you on the podcast on the internet, and I live in Bel Air, Maryland. My question is regarding electromagnetic waves. I understand the electromagnetic waves propagate through space at the speed of light, but how about magnetic waves alone? Namely, when you turn on an electric magnet and pulse it, does the electric pulse travel at the speed of light? I thank you and have a great day.
Well, the answer is yes. Both electricity and magnetism travel at the speed of light. In fact, what was the breakthrough that Maxwell made? One of the greatest breakthroughs in the history of all of physics is when Maxwell realized, I got to take a short commercial break. Well, after the break, I'm going to talk about one of the greatest insights in the entire history of physics. An insight that led to Einstein's theory of relativity, an insight which is unfortunately very not known by the average person, but which makes possible many of the wonders in your living room. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Give us a call at 612-564-8135. Before the break, we mentioned that something happened about 150 years ago, one of the greatest insights in the history of physics took place. What was that? Well, first of all great scientists have had that flash of insight which changes human history. One of the greatest insights of all time took place when a 23-year-old gentleman by the name of Isaac Newton, a young student at Cambridge University, watched an apple fall. He saw the moon, and then he asked that key question, if an apple falls, does the moon also fall? And from that, he got the theory of gravity, the theory of mechanics. Einstein, when he was 16 years old, had that similar insight when he asked himself a simple question: can I outrace a light beam? The answer to that took him 10 years, and he created the theory of relativity. Well, there's another great insight done by James Clerk Maxwell of Cambridge University in the 1860s. Most people don't know this insight. What he did was he calculated the motion of a moving electric field. Like you take a rod, electrify it by rubbing it, and wave it. It creates a wave. He calculated the fact that that wave creates a magnetic disturbance, and that magnetic disturbance then creates an electric one, and it goes back and forth, back and forth. So an electric disturbance creates a magnetic one, creates an electric one, creates a magnetic one, ... And he realized that what you get from this is a traveling wave. Then he calculated the speed of this traveling wave, and he was floored, absolutely floored, when he discovered that the speed of vibrating electric and magnetic fields is the speed of light. And then he made that prophetic observation: this is light. What is light? Ever since humans first opened their eyes, we've wondered, what is this mysterious thing called light? Well, it was worked out by one of the greatest insights of all time when James Clerk Maxwell, calculating the speed of vibrating electric fields and magnetic fields, found out that both of them vibrate together at the speed of light. And then he made one of the greatest insights of all time. This is light. That's what light is. It's an electromagnetic field. And by calculating the speed of it, Einstein was able to realize that that speed is constant in all moving frames. That gave us special relativity, which in turn gives us the atomic bomb and the energy of the stars. That's why the sun shines. Amazing. Simple insights. Insights that in principle children could have propel human history. Unfortunately, the only people who don't know this are professional historians. Okay, well, let's take the next listener phone call.
My name is Ozma Cunnington, and I'm calling from Chehalis, Washington. And the question I have is the dinosaur bones and things they find on the Earth. Could those have been in matter that they built the Earth with and never really came from our Earth? Thank you very much, and I love your program. Bye.
Okay, well, I didn't quite understand the question you raised, but let me try to answer it. First of all, the dinosaurs ruled the Earth for about 200 million years. We humans have only been on the Earth for about 100,000 years. But the dinosaurs ruled the Earth for 200 million years, and they suddenly vanished 65 million years ago. And we think it was an extraterrestrial object, an asteroid or a meteor, which hit the Earth and created a cloud of debris so great that it blanketed the sun, dropping temperatures around the planet Earth so that plant life would die, plant-eating dinosaurs would starve, and meat-eating dinosaurs would also die as a consequence. So even though the dinosaurs themselves came out of the Earth, came out of debris that made the Earth, an object from outer space destroy the dinosaurs. And then I think what you're getting at is then the question is, well, where did the dinosaur material come from? And that also originally came from outer space. Because where did the Earth come from? To the best of our knowledge, the Earth is about 4.6 billion years old. The Earth and the Sun and the planets were formed out of the same protostar, and so the whole solar system was created about 4.6 billion years ago by the accumulation of dust, which eventually accumulated rocks, and these rocks collided with other rocks and meteors that eventually gave us the Earth. Now, we can actually see this process in outer space by looking at baby planets in formation. We can actually do that now by examining baby planets in formation throughout the universe. We see that the basic pattern is the same. First, you have a dust cloud, a spherical dust cloud, which will eventually become the sun. As it collapses, it forms a disk that is rotating very rapidly. At the center of the disk, you have the sun, and then the planets are condensed out of the disk. The planets then form out of the condensation of the disk by random collisions of debris getting larger and larger. Eventually, gravity takes over, so these planets begin to gravitationally attract other large objects, and you get collisions, and that's where the Earth came from. The dinosaurs came from that, but the dinosaurs themselves were eventually wiped out by another piece of debris. So our solar system is not fully formed. That is, it's in a continual process of formation. We still have the debris left over from the ancient solar system, and that debris is potentially dangerous. For example, it wiped out the dinosaurs. And as I mentioned in my book, The Future of Humanity, unfortunately the dinosaurs did not have a space program. And because of that, they're not here today to talk about it. We do have a space program, and so perhaps one day we may be able to avoid the fate that afflicted the dinosaurs. Okay, well that's it for Science Fantastic. back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And in this hour, once again, we're going to throw the lines open because this hour is dedicated to you. Okay, let's move on now and take the first listener phone call.
Yeah, this is Robert, local station WMKT, Traverse City. My question is that I understand that time slows down the faster you travel. So if say an astronaut goes into space and he's traveling 1,000 miles an hour and he comes back to Earth, well, maybe he's only like 2 or 3 seconds younger than we are. Does that mean that the past, and obviously he's here with us, does that mean that the past can exist at the same time as the future? In other words, what I'm asking is my grandmother in 1920 getting married right now at the same time I'm here? I hope you can answer that because, it just seems a little funny to me. Thank you.
Yeah, well, you have the right question. However, the answer is a little bit more subtle than you may realize. Einstein once joked that he put a clock everywhere in the universe, at a different place everywhere in the universe, each clock beating at a different rate. But he said he was so poor, he could not afford a clock of his own. He had to look outside his window to see the clock tower to find out what time it was. And that's exactly the way he viewed it. You put a clock everywhere at every point in the universe, each clock beating at a different rate. Okay? So you're right. The astronauts, when they go into outer space, they come back a fraction of a second younger than a twin that is on the planet Earth. And if you want to find out exactly how much time has distorted, take the velocity of an astronaut, that's 18,000 miles per hour going around the Earth. Divide by the speed of light, that's 186,282 miles per second. Okay, so the velocity of the rocket divided by the speed of light, square it, and you find an incredibly small number. That is the ratio at which time is slowing down. The velocity squared divided by the speed of light squared. It is a very tiny number. And you can see immediately that the astronauts, when they come back, are like a microsecond, less than a microsecond younger. So it's a very, very small effect. Now, if you boost that rocket, however, up to near the speed of light, let's say, hypothetically, then it would be, let's say, 90% the speed of light divided by the speed of light, which is 90%. Now we're getting somewhere. Now we find out that time slows down so much that it's actually appreciable. Now, you ask yet another question. Does that mean that you can meet your relatives who have passed away in the past? Does that mean you can meet your children when they're all grown up, decades into the future? And the answer is no. Again, imagine putting a clock every point in the universe, each clock beating at a different rate. But does that mean that one clock on the Earth can immediately talk to another clock in the past? And the answer is no. You have to bring the clocks together. And that's the key. When you bring the clocks together, then they start to beat at the same rate because they're traveling at the same velocity. So in other words, you cannot meet your mother before you're born. Sorry about that. Now, there is a loophole, however, in Einstein's equations, which may give you the possibility of meeting your mother before you're born. And that is if you can drill a hole through space through a black hole. That is perhaps one of the only ways in which you can twist time so much that you can actually go back into the past. This is still controversial, of course, but get a copy of my book, Physics of the Impossible, and I give you the pros and cons of what would happen if one day we could meet our parents before we're born. Okay, let's move on now and take the next listener phone call.
Hello, Dr. Kaku. This is Eddie Bryant from Murphy, North Carolina, streaming from your website. My question is this. I was reading a paper published in November 2017 called Reversing the Thermodynamic Arrow of Time Using Quantum Correlation. in which they were able to violate a principle of the laws of thermodynamics where they entangled two particles and that certain initial conditions allow for the heat flow from cold to hot, essentially reversing the arrow of time. As we all know, entropy seeks equilibrium, and in this case, that doesn't happen. I'm wondering if you can please expand on this paper in order to demystify the substance of the research for us less educated. And from that paper, I was curious about any theoretical possibilities in the future to entangle particles in time, thus allowing particle B, made after particle A, to go back in time to a state it never existed in, quantifying time travel a little bit more than what this paper suggests, which I'm gathering is just an appearance of some violation. I've seen plenty of videos on how to entangle photon particles, but I'll leave anything more complicated than that up to you guys. I know this isn't a possibility now, but that paper led me to be curious if it was at all possible. Cue in your book, Physics of the Impossible. A great read. Thanks for the time. I'll be listening for your answer.
Well, the answer to your question is yes. Next question. Well, no. Let me give your answer a serious, thought-provoking response. First of all, let's talk about the second law of thermodynamics. Let's talk about entropy. Let's talk about entanglement. And let's put them all together and see whether you can go backwards in time and build a time machine from this. First of all, we have the second law of thermodynamics, which basically says that in an open system, chaos always increases. Things rust. Eventually, people die. Things fall apart. Things get corroded, they rust, they disintegrate. That's the second law of thermodynamics. Oh, we have to take a short commercial break, but then after the break we'll talk about, well, is it possible to live forever by reversing the laws of thermodynamics? We'll answer that question after the break. Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, well, this hour is your hour. Well, before the break, we had a very interesting question, and let's break it down into its components. First of all, we have the second law of thermodynamics, which says that in any open system, things fall apart. We all know that. Things rust. Things get stained, things crumble, things die. In fact, that's the reason why we die. We die because chaos eventually takes over. Genetic mutations build up in our cells over time. Cells get sluggish and eventually don't function, and then we die. That's why we die, the second law of thermodynamics. However, I mentioned an open system. This means that in a closed system, you can temporarily reverse the arrow of time. So the arrow of time points toward chaos. The arrow of time points toward death, destruction, collapse, calamity. However, that's in an open system. Let's talk about a closed system whereby you can actually make changes in the arrow of time. There's a loophole in the laws of thermodynamics, and that is if you apply energy from the outside, mechanical energy from the outside. So, in other words, some people ask the question, if we have the second law of thermodynamics on the Earth, then why do we exist? Humans are obviously smarter than rocks. So, if the universe naturally creates rocks, how were we created? We represent a violation of the laws of thermodynamics. We are intelligent. We can sing, dance, we can connive, we can build atomic bombs, we can build rocket ships. Rocks cannot. Therefore, it seems to an average person that the laws of thermodynamics are violated. No. If you add energy from the outside, you can locally reverse the laws of thermodynamics. And where does that energy come from? Ta-da! It comes from the sun. The sun's energy provides us with nutrients which allow us to therefore reverse the laws of thermodynamics locally. Now this means, of course, that the Earth will eventually die. Sorry about that, but that's a law of physics. However, it means that temporarily Locally, we can reverse the laws of thermodynamics, and bingo, here we are. Sunlight makes possible photosynthesis. We eat the plants that arise from photosynthesis. We metabolize these plants and get energy, and that's where we come from. That's why we have evolution. That's why we can have things that are intelligent arise from rocks. So, then the questioner asked yet another question. What about the quantum theory? So far, we've only talked about classical physics, that is, the physics of Isaac Newton. The physics of Isaac Newton is based on the idea that every atom is like a billiard ball, a tiny steel ball. You know exactly where that ball is. But in the quantum theory, there's uncertainty. You don't know exactly where that ball is at any given time. But, yes, even under the quantum theory, the second law of thermodynamics applies because we're dealing with the motion of large amounts of atoms. On average, if you average over billions of atoms, the laws of quantum mechanics gradually disappears. This is the reason, for example, why you can't be two places at the same time. Atoms can do that. Electrons can do that easily. Electrons can be two places at the same time, but you cannot. Because you are very big, that's why. You average over trillions upon trillions of atoms, each atom being many places at the same time, and bingo, here you are. You have the illusion. You have the illusion that you are exactly at one place at one given time. That's the view that Einstein had. That's the view that Isaac Newton had, but sorry about that, it's wrong. At the quantum theory, you don't really know where the electron is. That's called the Heisenberg uncertainty principle. This means also that you can have two electrons that are entangled. That is, they vibrate together, and then if you separate them, there is an umbilical cord, an invisible umbilical cord that emerges connecting them. So what happens to one electron inevitably affects the other electron. That's called entanglement. Now, the questioner asked a question as follows. Can all this quantum gibberish reverse the second law of thermodynamics? And my personal point of view is no, because the second law of thermodynamics operates on an average, averaging over trillions upon trillions of atoms, where quantum effects are gradually washed out. That's why we cannot be two places at the same time. Now, when I talk about this to audiences, I mentioned, therefore, that our universe could actually split perhaps into two universes because of the quantum principle. And then people ask the question, does that mean that Elvis Presley is still alive in another universe? And the answer is, believe it or not, you cannot rule it out. There's a finite probability of other universes being out there in which people that have died in our universe are still alive in another universe. That sounds preposterous, but hey, that's called the quantum theory. Okay, well, let's move on to the next listener phone call.
Hi, Professor. My name is Francine. How does an earthquake cause a tsunami? That deadly thing that hurts a lot of people. Bye.
Well, you ask a question that's in the news because, of course, the Earth is geologically active, and sometimes big earthquakes create tsunamis which can destroy huge chunks of real estate. Look what happened to Fukushima in northern Japan. We had an earthquake that erupted, caught many seismologists off guard, created a huge tidal wave which inundated the city, and 10,000 people lost their lives. This happens in Indonesia and the Philippines. And the question that the questioner asked is, how? How are tsunamis formed? First of all, there are two major types of earthquakes. One earthquake is caused when two fault lines slide horizontally past each other, like the San Andreas Fault. You realize that San Francisco and Los Angeles, millions of years from now, will be right next to each other. That's right next to each other, because Los Angeles is going north relative to San Francisco, which is going south. So California is being ripped apart. That's called a sliding fault. And sliding faults do not create tsunamis. So if this fault is underneath the ocean, one fault would go north, the other fault would go south, and no tsunamis are formed at all. However, if you live in the Seattle, Portland area, you have to be worried about the Cascadia Fault, not the San Andreas Fault. And the Cascadia Fault is a subduction fault where one fault line goes underneath another fault line. That's called subduction. When that happens abruptly, that means the floor of the ocean floor itself drops, leaving a huge gap, which is then filled by water from the neighboring area, creating a tidal wave. So you can actually create a mini tidal wave in your bathtub tonight. Next time you're in your bathtub with your rubber ducky, put your two hands underneath the surface of the water, and then suddenly drop and raise the other hand. By dropping one hand, raising the other hand, you create a tiny mini tidal wave on the surface of your bathtub right next to your rubber ducky. That is called a tidal wave or tsunami created by a subduction fault. And we have them, and they're terrifying, off the coast of the United States in the Cascadia Fault. Now, we know the Cascadia Fault has erupted in geologic times by actually looking at the ecology of the Seattle area. Some geologists have noticed the fact that there seem to be dead forests, trees that died centuries ago, many years ago, that died because of salt water. Salt water inundated that area, but everywhere you look, there's no salt water. And then you begin to realize, if you are so many miles away from the coastline, it must have been a huge tidal wave that sent salt water into the coastline, killing all these forests. Once again, you are listening to Science Fantastic. Welcome back to Science Fantastic with Professor Michio Kaku. You know, whenever I walk outside, whenever I see the sun, the clouds, the oceans, I pretty much know where everything came from. I know why we have air. I know how old the mountains are. I know where the oceans came from. I know why the sun shines. It's not a mystery to me. And sometimes I wonder, how can you go through life walking down the street wondering, gee, what does it all mean? Where does it all come from? Why does this happen? Why does that happen? And never know the answer. Well, unfortunately, that's the way it is with most people, but perhaps not for you. Maybe you want to know why. Why do things happen the way they do? Why be a leaf in the wind, being blown by forces beyond your control, not in control of your own destiny? You know, that's one of the things I learned growing up. If you want to control your own destiny, then learn about the world around you. Don't be a leaf blown in the wind, going whichever way the wind blows, not being in control of your own fate. Why don't you control your own fate? Learn about the world around you so it's not mysterious, so you don't get caught off guard. Okay, well, let's move right on now and take the next listener phone call.
Hello, my name is Jay. I listen to your great show on WNDV in Daytona Beach, Florida. I have a question about names. We have names for our planet, Earth, our moon, Luna, our star, Sun, our galaxy, Milky Way. But do we have a name for our solar system? With so many planets orbiting other stars, do you think we may have to give solar systems names soon? Thank you for your interesting radio show, Professor Kaku, and I really enjoy it. I look forward to more shows. Thank you.
Well, you ask a very interesting question about namings, and it turns out that recently some astronomers have yelled and screamed at other astronomers precisely about the naming of objects in outer space. You know, we have the Astronomical Union, which helps to regulate the naming of things, but it becomes very contentious because some astronomers have a sentimental tie with certain names, and yet these names may not be totally scientific. For example, the most famous example of this is Pluto. Now, by rights, Pluto should perhaps not be a planet at all. Well, let's take another short commercial break, and after that we'll talk about the naming of things. Where do these names come from? Is Pluto really a planet? And is there Planet X out there? Who's going to name Planet X? Welcome back to Science Fantastic with Professor Michio Kaku. Well, we had a call coming in about naming things. How do we name things? And it's actually rather contentious. First of all, many of the stars that you see at night, many of them have Arabic names. Algol, Altair. Why? Because, well, after the fall of the Roman Empire, much of the knowledge of astronomy went to the Arabs. They were the ones that carefully transcribed that information. Algebra, for example, was preserved from the Greeks, and algebra, Altair, Algol, the names of the stars, yes, a lot of them have Arabic names precisely for that reason. So, with so many planets out there now, how do we go about naming things? Well, usually the people that discover these things have first dibs on making the name for them. However, solar systems, to my knowledge, do not have a name. However, solar systems going around a certain star have a name. We have Proxima Centauri, for example. Alpha Centauri is a triple star system. Proxima Centauri B is one of the planets going around Proxima Centauri. Proxima Centauri B is the closest planet that we have identified that is near the Earth. So the ABC then gives you the nomenclature of the different planets within that solar system. Now, this process of naming things actually became rather contentious over the issue of Pluto. So let me explain that really quickly. First of all, Pluto was discovered around 1930. And Pluto was thought to be a planet because scientists were cataloging planets. They went all the way out to Uranus, Neptune, and the next one logically would be another planet. But Pluto is an oddball. It's probably not a planet in the ordinary sense of the word at all. We have the gas giants, Jupiter, Saturn, Uranus, Neptune, gas giants which are huge, and Pluto, which is more like a moon than a planet. And it's not even a gas giant at all. It's an oddball out there. And it's really part of the Kuiper belt. The Kuiper belt of comets. Kuiper himself was an astronomer who theorized the existence of a belt of comets surrounding our solar system, and Pluto is thought to be a member of the Kuiper belt. But in deference to those astronomers who insist that Pluto is a planet, we call it a dwarf planet. So there are dwarf planets within the Kuiper belt of comets. Now that's kind of confusing, isn't it? But just remember that Pluto really is not like one of the other gas giants. Now it gets more complicated now, because now we may have Planet X. Planet X seems to be a gigantic planet, about the size of Neptune, way out there. And so the nomenclature is starting to get more and more complicated. There's also another object identified out there called the Goblin, nicknamed the Goblin. And that seems to be an object almost the size of Pluto, way beyond the orbit of Pluto. So once again, to make sense of all these things, there is an astronomical body that officially gives names to all these objects. And that's where the nomenclature comes from. And again, usually the people who discover that object have first dibs to coin a name for that object. But hey, politics is politics. There's going to be a politics even in the naming of planets and stars. Okay, well, let's move on now to the next listener phone call.
Hi, this is Ken. I'm calling because I'd like to ask about Albert Einstein's contributions. They say he's a genius, but at the same time, it's debatable whether or not, how big of a genius he was, because he got many things wrong, including the background radiation, quantum mechanics. The same thing is true of also Rosalind Franklin. It's my understanding she may have discovered the structure of DNA, but at the same time, Francis and Crick actually contributed substantially to what Franklin already had. So, people villainize Watson and Crick, but in actuality, they were the ones who really discovered the DNA molecule. So I'd like to ask you to clarify that.
Well, first of all, you have a point, and that is we're all human. And even though we say that, for example, Isaac Newton or Albert Einstein were geniuses, what does that really mean, given the fact that they're also human and they also made mistakes as well? You can go through the works of Isaac Newton, for example, and find many mistakes there, but he ranks as perhaps one of the greatest scientists of all time. Starting from nothing, literally nothing, he created the understanding of the mechanical universe and the forces of today. Well, let's take a short commercial break, and after the break we're going to continue a discussion of, well, who really is a genius and who gets credit for making these big discoveries. Welcome back to Science Fantastic with Professor Michio Kaku. Well, just before the commercial break, we had a question about giving credit. I mean, was Einstein really a genius, given the fact that he did get some things wrong? Well, yes, I think he is a genius, but I think we have to use words more carefully, because ultimately we're human. Ultimately we do make mistakes, but I think perhaps there's a continuum of ranking of the great scientists, and of course this is still very subjective. Number one on the rank of all scientists, the greatest scientist of all time, would probably be Isaac Newton. He was the one starting from nothing. A world that was full of witchcrafts and demons and goblins. He started from that world and created mechanics, a physical understanding of the universe itself, laws that we still use today when sending space probes throughout the universe. That is incredible. Discovering calculus, discovering the basic laws of color, understanding the laws of motion. Incredible. Next would be Einstein. He took the calculus of Newton, and from that was able to extract physical principles which gave us special relativity and general relativity. And yes, all of them made mistakes. You can read Principia, and, well, Principia is a classical tome. It's not quantum mechanical. And the same thing with Einstein's theory. There's no mention of quantum mechanics, but I don't think we can be too harsh criticizing Einstein for neglecting the quantum theory. Einstein never said that the quantum theory was wrong. He just, A, didn't like it, and B, thought that ultimately it would be derived from a higher theory, the unified field theory. So again, people get Einstein's mistakes incorrect. He never said that quantum mechanics was wrong, that is the theory of the atom. He said it was incomplete. He said that there must be a higher theory which gives quantum mechanics as a derivative. And also about the DNA pictures. Yes, Rosalind Franklin did not understand the double helix nature of what she was doing. She was the one who took the electron micrographs, which made it possible for other people to say, aha, it's a double helix, here's how it all fits together. No, she did not do that. But she was part of the discovery. And so you have to give her credit for being part of the discovery that propelled DNA to the centerpiece of biology. So once again, I think we're all human. There's a continuum of contributions of things. And when you look at one given tremendous achievement, usually it's a contribution of many people. Nobel Prize winners, in all their humbleness, usually give credit to all the other scientists who also participated in that search. And unfortunately, many of them never win the Nobel Prize. Think of the Nobel Prize. Think of all the scientists who never won the Nobel Prize because they never got the credit that they deserved. Okay, well, let's move on now to the next listener phone call.
Hello, this is Armand from Queens, New York. I listen to you on YouTube. I was wondering, I saw an article that said that the Chinese have an AK-47. It's like a laser that can light people on fire from a mile away, pretty much, or a half mile, something like that. Do you know anything about that? And do you think that's possible? If so, all right, have a great day. I love the show. Peace.
Well, first of all, are the Chinese working on lasers? Yes, but for that matter, are we working on lasers? And the answer to that is yes. Is it possible to create a laser that can start a fire from a long distance? And the answer to that is yes. In fact, we've been doing that for decades. I even have a photograph in my picture file of a GI, this is back in the 70s, I think, with a rifle, a laser rifle, firing a laser beam sufficient to set off explosive many hundreds of feet away. So instead of getting a match and lighting the fuse of an explosive and then blowing yourself up in the process, why not simply use a laser gun and shoot that laser beam and ignite that explosive? And we did this decades ago, back in the 1970s, as I recall. And so, yes, other countries are working on these things too. We shouldn't be naive to think that only certain countries are working on this technology. But the bottom line is, of what use? Now, what practical use are these technologies? Can they be controlled? Will they get out of control? These are the bigger questions. And for the most part, lasers in warfare have been a big disappointment. It turns out that laser power dissipates when it goes through air, for example, meaning that the power of the laser beam diminishes considerably, meaning that the Buck Rogers idea of laser guns and things like that, still possible, but more expensive and more unstable than we originally thought. That's why we don't have ray guns, for example. It would simply cost too much and require a power supply that we don't have to create a ray gun. So the idea of a ray gun never materialized for practical considerations. You need a power pack, a tiny power pack that you can fit in your hand, for example, to energize a ray gun. And unfortunately, we don't have that. We don't have batteries. We don't have portable power packs sufficient to drive something like a ray gun. So the idea of going into battle with a laser ray gun, battling away and defeating your enemy is still a dream rather than a reality. We simply don't have a portable power pack sufficient to drive ray guns. Well, unfortunately, that's it for Science Fantastic.